Look up at the night sky. Even with the naked eye, you can see stars scattered like diamonds on black velvet, each one a sun, many with their own worlds. But let's pull back the lens, way back, beyond our solar system, beyond the Milky Way, past galaxy clusters stretching billions of light years across. What you're left with is the observable universe, a vast, expanding tapestry born from a single, unimaginable event nearly 14 billion years ago, the Big Bang. In its earliest moments, the cosmos was a seething chaos of energy, too hot for atoms to even form. And then, almost as suddenly as it began, everything changed. In less time than it takes to blink, the universe cooled just enough for the very first elements to emerge. Hydrogen, helium, tiny traces of lithium, the lightest and simplest building blocks of everything we see around us. They are the silent architects of stars, planets, and life itself. But here's the extraordinary mystery scientists are still racing to solve. How did these primordial ingredients actually form? We know they appeared within the first few minutes after the Big Bang, forged in a furnace of cosmic creation. Yet the precise how and why remains one of the greatest puzzles in all of physics and cosmology. This isn't just some abstract academic debate. Understanding the origin of the light elements means understanding where everything, including each of us, ultimately came from. It's a question that reaches back to the very dawn of time. In this video, we're going to explore 30 captivating theories that attempt to unravel this cosmic whodunit. Some are widely accepted, some are controversial, others walk the fine line between genius and madness. Together, they form a thrilling intellectual adventure, one that will take us from the birth of the first atomic nuclei to the cutting edge of today's astrophysical research. So settle in, we're about to journey back to the beginning of everything. But to truly appreciate how strange and wonderful this story is, we have to start with the theory that laid the foundation for all others. This is the cornerstone, the benchmark against which every alternative is measured. It's called Big Bang Nucleosynthesis, or BBN for short. Picture the universe not even a second old. It's an impossibly dense, hot soup of fundamental particles, quarks and gluons bubbling in a primordial plasma. As it expands and cools at a ferocious rate, these quarks begin to bind together, forming the first protons and neutrons. For a brief window, roughly between 1 second and 3 minutes after the Big Bang, the conditions become just right for nuclear fusion to begin. It starts with the simplest partnership imaginable. A single proton and a single neutron combining to form a deuterium nucleus, a heavy isotope of hydrogen. This is the crucial first handshake, the gateway reaction. Without it, nothing else can happen. Once deuterium exists, a frantic chain reaction unfolds. Deuterium nuclei collide and fuse into helium-3. More reactions build helium-4. In a cosmic frenzy lasting only a few minutes, nearly all the available neutrons are locked up into these new helium-4 nuclei. And then, just like that, it's over. The universe has expanded and cooled so much that the particles are now too far apart and moving too slowly to overcome their mutual electrical repulsion. The furnace is shut down, leaving behind a cosmic ash of about 75% hydrogen and 25% helium by mass, with vanishingly tiny traces of lithium. The beauty of this theory lies in its breathtaking precision. The predictions it makes for the exact abundances of these light elements are exquisitely sensitive to one key parameter: the density of ordinary matter in the early universe. Alter that density slightly, and the predicted amounts of helium, deuterium, and lithium change dramatically. The fact that these predictions, made decades ago, align so perfectly with what we actually observe in the oldest corners of the cosmos is arguably the single strongest piece of evidence we have that the Big Bang actually happened. This incredible work is credited to a brilliant and charismatic physicist named George Gamow and his colleagues Ralph Alpher and Robert Herman. In 1948, they published a seminal paper, often whimsically called the Alpha-Beta-Gamma paper, a play on the first three letters of the Greek alphabet and the author's surnames. Alpha, Beth, and Gamma, though Hans Bethe was added as a co-author as a joke, his name fitting the theme. They were the first to seriously calculate how the elements could have been forged in the hot early universe, setting the stage for everything that followed. Their theory wasn't perfect. It couldn't explain elements heavier than helium, but it provided the crucial framework. It gave us a startlingly clear snapshot of our universe in its infancy, a mere 3 minutes old. Yet for all its predictive power, Standard Big Bang Nucleosynthesis isn't without a few lingering puzzles. The most stubborn one involves a specific tiny element, lithium. You see, the model predicts a certain amount of lithium-7 should have been created in those first 3 minutes. But when we look at the oldest stars in our galaxy, stellar relics that formed from that primordial hydrogen and helium, they show only about a third to half of the predicted lithium. It's a small but persistent gap, a nagging detail that suggests our picture of the universe's first moments might be just a little bit incomplete. This is where our second theory enters the stage, offering a fascinating twist on the classic narrative. It's called the inhomogeneous Big Bang model. The standard model assumes the early universe was a remarkably smooth, uniform soup, but what if it wasn't? What if, instead of a perfectly blended broth, the infant cosmos was more like a fizzy, bubbly soda? This theory proposes that in the incredibly dense environment just after the Big Bang, there may have been significant fluctuations in density. Certain regions could have been much denser than others, creating a patchwork of high-pressure zones amidst a background of more average density. Think of it as a cosmic foam. Now, how would this bubbly universe affect the creation of elements? Neutrons are the key. In the standard model, free neutrons decay very quickly. They have a half-life of only about 10 minutes, so the nucleosynthesis window is a race against time to incorporate them into stable nuclei before they vanish. In a perfectly smooth universe, this process happens at a uniform rate everywhere, but in an inhomogeneous one, the story changes dramatically. In those ultra-dense pockets, the sheer concentration of particles would have allowed protons and neutrons to find each other and fuse into helium much more efficiently and rapidly. They'd use up the available neutrons faster. Meanwhile, in the less dense regions between these pockets, the process would be slower and less complete. This uneven playing field could have major consequences for the elements we end up with. The faster fusion in the dense zones might leave behind a different mix of byproducts, potentially altering the final amounts of delicate isotopes like deuterium and, most notably, that problematic lithium-7. By tweaking the size and distribution of these proposed primordial bubbles, physicists can adjust the model's output, sometimes achieving a much closer match to the lithium levels we actually observe in the ancient universe. This model doesn't overthrow the standard BBN. It builds upon it, adding a layer of complexity to explain an anomaly. It suggests that the cosmos might have had a lumpy, textured beginning, a far cry from the perfectly smooth start we often imagine. While evidence for such strong initial inhomogeneities remains elusive, the theory stands as a powerful reminder that even our most successful scientific models can often be refined by looking at the data just a little bit differently. But to understand the next layer of this cosmic mystery, we have to rewind the clock even further. We need to travel back to a time before even protons and neutrons existed, to a universe barely a microsecond old. This brings us to a truly mind-bending frontier, the quark-hadron phase transition. The name sounds complex, but the concept is a dramatic one. Imagine the universe at this stage isn't filled with the familiar particles we know, but is instead a seething, ultra-hot plasma of free quarks and gluons. Quarks are the fundamental building blocks that normally make up protons and neutrons, but here, the energy is so unimaginably high that they cannot stick together. They zip around freely in what physicists call a quark-gluon plasma. Then, as the universe expands and cools past a critical threshold around 2 trillion degrees Celsius, a monumental phase change occurs, much like steam condensing into water. In an instant, the free quarks and gluons are forced to combine, to freeze out, and bind together into the first composite particles, protons and neutrons. This is the quark-hadron phase transition. Now, the fascinating part of our third theory is the question of whether this transition happened perfectly smoothly. Could this sudden condensation of matter have created tiny ripples or imperfections in the distribution of protons and neutrons? Some models suggest that as the universe underwent this dramatic shift, it might have created slight inhomogeneous pockets where the new protons and neutrons were clustered a little more densely, and other regions where they were more spread out. These initial fluctuations, imprinted into the fabric of matter mere microseconds after the Big Bang, would then have been carried forward in time. When the nucleosynthesis window finally opened a few minutes later, this pre-existing patchwork could have set the stage. In regions with a higher density of neutrons, the fusion process might have run faster or more efficiently, potentially producing a slightly different yield of helium, deuterium, and lithium than in the less dense areas. It's a theory that connects the physics of the unthinkably early universe, governed by quantum chromodynamics, directly to the observable fossil record of the light elements we see today. While the Standard Model assumes a smooth transition, this idea opens the door to a more dynamic and textured beginning, suggesting that the seeds for the lithium problem might have been sown long before the first atomic nuclei ever fused. Now, let's introduce a ghostly character into our cosmic drama, one that floods the universe yet is famously difficult to detect: the neutrino. This brings us to our fourth theory, which asks a subtle but profound question. What if the very first elements were shaped not just by the blazing heat and frantic collisions, but also by a silent, invisible sea of particles left over from the Big Bang itself? We're talking about the cosmic neutrino background. To understand its potential influence, we need to revisit a critical moment in the early universe, the moment that set the stage for everything to come. About 1 second after the Big Bang, a pivotal event occurred called neutron decoupling. At this instant, the universe cooled enough that a crucial process, which had been keeping the number of neutrons and protons in balance, effectively shut down. This process is known as weak interaction, and it's mediated by force-carrying particles called W and Z bosons. Up until this 1 second mark, these interactions were constant and energetic. Neutrons and protons were constantly converting into one another. A neutron could turn into a proton by emitting an electron and an anti-neutrino, and a proton could turn into a neutron by absorbing an electron and emitting a neutrino. This dynamic dance kept the populations of protons and neutrons in a state of equilibrium. But as the universe expanded and the temperature plummeted, the energy of the average particle dropped below the threshold needed for these conversions to happen easily. The weak interaction, true to its name, became too weak to keep up with the rapid expansion. The reaction rate slowed to a crawl, and the conversions effectively stopped. The ratio of neutrons to protons was frozen in place. This ratio is absolutely critical because neutrons are the fuel for building anything heavier than hydrogen. The number of neutrons available at this 1 second mark directly determines how much helium can be forged during the nucleosynthesis window a few minutes later. More neutrons mean more helium, fewer neutrons mean less. This is where the cosmic neutrino background comes in. In the Standard Model, we assume that after decoupling, these neutrinos simply streamed away into the cosmos, never to interact significantly with matter again. But this theory suggests their influence might not have ended so cleanly. This background is a relic sea of these particles, a fossil from that first second, still permeating every cubic centimeter of the universe today. There are billions of them passing through your thumbnails every second, completely unnoticed. The theory proposes that even after decoupling, this dense background of neutrinos and antineutrinos could have very subtly continued to interact with the dwindling population of free neutrons. A free neutron is unstable and will decay into a proton with a half-life of about 10 minutes. But what if the presence of this neutrino slightly accelerated or decelerated that decay process for some neutrons? Even a tiny, almost imperceptible change in the rate of these weak interactions during this delicate window could have shifted the final neutron-to-proton ratio by a small fraction. And in the high-stakes, precision-driven world of Big Bang nucleosynthesis, a tiny shift is all it takes to alter the predicted abundances of helium, deuterium, and lithium. The challenge, of course, is that this influence is incredibly difficult to prove or quantify because detecting the cosmic neutrino background directly is one of the greatest experimental challenges in all of physics. These particles interact so infrequently with matter that building a detector to observe them is a monumental task far beyond our current technology. So while this theory offers a beautifully subtle and elegant mechanism for tweaking the early universe's recipe, it remains, for now, a compelling hypothetical layer to our understanding of those first fragile minutes. But our universe's infancy might have been even more chaotic and violent than we've described. To explore this possibility, we turn to a theory that introduces a truly cosmic agitator into the primordial soup, the gravitational wave. This leads us to our fifth compelling idea, the gravitational wave primordial soup theory. We often picture the early universe as a hot, dense, but relatively smooth expanding fireball. However, many cosmological models suggest its first instants were likely punctuated by periods of incredibly violent activity. Events like the rapid inflation of space-time itself or the collision of nascent universes in a multiverse foam could have sent powerful ripples echoing through the fabric of reality. These ripples are gravitational waves, not unlike the ones we detect from merging black holes today, but on a scale and intensity that is almost impossible to comprehend. They would have been waves of pure gravity racing through the seething quark-gluon plasma. Now imagine a perfectly still pot of water. If you gently heat it, it will eventually simmer in a predictable way. But if you were to violently shake that pot, you would create a churning, turbulent mess with swirling eddies and sudden, localized hotspots. This theory proposes that these primordial gravitational waves did exactly that to the universe's first matter. As they passed through the plasma, their immense energy would have churned and compressed it, creating temporary, fluctuating regions of extreme density and temperature amidst the overall cooling background. In these brief, intense hotspots, the conditions for nuclear fusion would have been dramatically enhanced. For a fleeting moment in these pockets of chaos, the frantic dance of protons and neutrons could have proceeded at a much faster and more efficient rate. Fusion reactions that might have struggled to occur in the average environment could have been given a powerful, localized boost. This isn't just about making more of the same elements, it's about potentially altering the very pathway of creation itself. These sporadic bursts of extreme energy might have allowed for different nuclear chains to briefly dominate, producing a slightly altered mix of isotopes. It could have led to tiny, unexpected overproductions of certain elements or underproductions of others, subtly changing the final cosmic recipe that froze into place once the universe cooled for good. The gravitational waves would have left no permanent chemical stain themselves. After stirring the pot, they would have continued on their way, leaving behind only their imprint on the elemental abundances. This theory provides a fascinating mechanism to explain small deviations from the pristine predictions of the Standard Model, like the lithium problem, by invoking the dynamic and turbulent physics of the very earliest moments, a time when the universe itself was ringing like a bell. Now, let's venture into one of the most speculative and thrilling ideas on our list, a concept that sounds like it's pulled straight from science fiction but is grounded in real theoretical physics. This is the theory of primordial black hole catalysis. To set the stage, we need to imagine a type of object that has never been conclusively observed but is a fascinating possibility predicted by many models: primordial black holes. Unlike the stellar mass black holes formed from collapsing stars or the supermassive ones at galactic centers, these would be true relics of creation, born from the fierce density fluctuations in the very first second after the Big Bang. They could range in size from smaller than an atom to as large as a mountain, all packed into an infinitesimal point of unimaginable density. Picture the universe just a few minutes old. The nuclear fusion party of Big Bang Nucleosynthesis is in full swing, with protons and neutrons frantically pairing up. But scattered throughout this seething plasma are these bizarre gravitational anomalies, microscopic black holes. Each one, despite its tiny size, possesses the same fundamental gravitational power as its larger cousins. Their gravity is so intense that it warps the space around them in a radical way. Now consider the challenge facing those early nuclei. To fuse, two positively charged protons must overcome their powerful mutual repulsion, a barrier known as the Coulomb barrier. They need to get incredibly close, which requires high speed and energy from violent collisions in the hot plasma. A primordial black hole sitting in this environment would act like a cosmic shortcut. Its immense gravitational field would accelerate any particle passing nearby to tremendous velocities. Imagine a proton wandering too close to one of these gravitational pits. It would be whipped around, gaining enormous kinetic energy as it falls inward, like a stone dropped into a well. If another nucleus is on a similar trajectory, the black hole's gravity could slam them together with a force and frequency far exceeding anything possible in the calm, expanding background of the universe. It would be a hyper-efficient nuclear fusion forge, a natural particle accelerator operating in the cosmos's first moments. This catalytic process wouldn't just make more of the same elements, it could open up entirely new nuclear pathways. The Standard model struggles to explain the precise amount of lithium-7 we see, and it cannot account for any beryllium at all in the primordial mix. But in the intense, gravity-boosted environment around a micro-black hole, fleeting reactions that are statistically negligible on a universal scale could become probable. Nuclei could be forced together in unique combinations, potentially creating just that tiny extra amount of lithium or even the first traces of beryllium, elements that would then be strewn into the cosmos as the black hole moved on or eventually evaporated. While these objects are still theoretical, their potential role as ancient, invisible architects tweaking the universe's first chemical elements is a breathtaking example of how the most exotic ideas in cosmology might hold the key to solving our oldest mysteries. This brings us to a theory that steps entirely beyond the known particles of the Standard model of physics, inviting us to consider a hidden, more symmetric layer of reality that might have left its fingerprint on the first elements. Welcome to the supersymmetric particle decay theory. To grasp this idea, we first need to understand supersymmetry, often nicknamed SUSY. It's a beautiful, mathematically elegant concept that proposes every known particle in the universe has a hidden superpartner. For every quark, there's a hypothetical squark. For every electron, a selectron. For every photon, a photino. This isn't just about doubling the particle zoo for fun. Supersymmetry solves several profound theoretical problems in physics, and many scientists believe it could be a key component of a more complete theory of the universe. Crucially, these superpartners are predicted to be much more massive than their ordinary counterparts, which is why we haven't found them yet. Our particle colliders simply haven't reached high enough energies to create them. But in the extreme, high-energy environment of the very early universe, these super-heavy particles would have been everywhere, produced in abundance in the seething plasma of the Big Bang. As the universe expanded and cooled, these massive supersymmetric particles would have become unstable. They'd decay, transforming into the lighter, familiar particles we know today. But here's where it gets interesting for our story of the first elements. The decay of these superparticles wouldn't have been a simple, quiet affair. It would have been a spectacular event, injecting a significant amount of extra energy and potentially even additional protons, neutrons, or other exotic particles into the primordial soup right during the critical window of Big Bang nucleosynthesis. Think of it like this: the standard model of BBN is a carefully choreographed dance happening on a cooling dance floor. The timing of the music and the number of dancers is exquisitely precise. Now imagine if halfway through the dance, a group of much larger, more energetic dancers burst into the room, danced wildly for a moment, and then vanished, leaving behind a different number of people and a lot of spilled energy. The entire routine would be thrown off. The decay of supersymmetric particles would act in a similar way, reheating the environment ever so slightly or altering the delicate neutron-to-proton ratio at a crucial moment. This injection of energy or particles could have significant consequences. It might slightly accelerate the fusion processes, or it could provide alternative pathways for nuclear reactions that aren't available in the standard model. This extra oomph could be just what's needed to tweak the final abundances of the light elements, potentially bringing the predicted amount of lithium into closer alignment with what we actually observe in the oldest stars. The precise effect depends entirely on the specific properties of the supersymmetric particles, their masses, their decay rates, and what they ultimately decay into. For cosmologists, this is a thrilling prospect. The persistent lithium problem might not be a flaw in our understanding of the Big Bang, but rather the first observational hint of physics beyond the standard model, a cosmic message from the supersymmetric era of the universe. It turns the mystery of the first light into a potential gateway for discovering entirely new laws of nature. But what if the very rules of the game were different back then? This brings us to our eighth and perhaps one of the most mind-bending theories on our list, the varying fundamental constants hypothesis. We take it as a given that the laws of physics are immutable, that the fundamental constants which govern our universe are, well, constant. The strength of gravity, the speed of light, the fine structure constant that dictates how tightly atoms hold onto their electrons. These are the fixed pillars upon which all of modern science is built. But what if that's only true for the mature universe? What if, in the frantic heat and density of the first few minutes, these so-called constants were actually shifting and settling into their modern values? This isn't just idle speculation. It's a serious proposition that emerges from attempts to unify the forces of nature, and it could provide a dramatic solution to our lingering elemental puzzles. Let's focus on one constant in particular, the strength of the strong nuclear force. This is the incredible glue that holds atomic nuclei together, overcoming the powerful repulsion between positively charged protons. In our universe today, it has a very specific, finely tuned value. But imagine if during Big Bang nucleosynthesis, this force was ever so slightly weaker. The consequences would be immediate and profound. Deuterium, that crucial first step, is a relatively weakly bound nucleus. If the strong force were weaker, deuterium would be even more fragile. It would break apart more easily, creating a bottleneck. The entire chain reaction would struggle to get started, resulting in far less helium being produced and leaving behind a larger surplus of deuterium and hydrogen. Conversely, if the strong force were briefly stronger, deuterium would bind more tightly. The fusion chain would proceed with ferocious efficiency, potentially locking up almost every available neutron into helium and leaving almost no deuterium behind at all. The same logic applies to other constants. The ratio of the gravitational force to the electromagnetic force, for instance, helped determine how quickly the universe expanded and cooled. A slightly different expansion rate would have shortened or lengthened the precious 3-minute window for fusion, drastically altering the final cosmic recipe. Now the million-dollar question is, how could we possibly test such a radical idea? The answer lies in looking across unimaginable distances and back into deep time. Astronomers do this by studying the light from the most distant objects we can see, quasars. These are incredibly bright beacons powered by supermassive black holes in the cores of ancient galaxies. Their light has traveled for billions of years to reach us. As this light passes through vast clouds of interstellar gas in the early universe, specific elements within those clouds absorb light at very precise wavelengths, leaving dark lines in the quasar spectrum like a barcode. By meticulously analyzing these absorption lines, scientists can measure the properties of atoms in the distant past, and here's where it gets astonishing. Some studies of this ancient light have tentatively suggested that the fine structure constant, which governs the strength of electromagnetic interactions, might have been ever so slightly different billions of years ago. The evidence is not yet conclusive and is hotly debated, but its mere possibility shakes the foundations of physics. If one constant could vary, perhaps others did too. This means the fossil record of the light elements, the specific amounts of hydrogen, helium, and lithium we measure, might not be a simple record of a single event under fixed rules. It could be a palimpsest, a layered message telling the story of how the universe itself cooled and settled into the stable, predictable cosmos we inhabit today. The varying constants hypothesis challenges our most basic assumptions and invites us to consider a truly dynamic dawn of creation, where the laws of physics themselves were still evolving. This idea takes the concept of a lumpy early universe and pushes it to its most extreme logical conclusion. We've already considered how simple density fluctuations could alter the cosmic recipe. But what if the very nature of matter itself was unevenly distributed? This is the core of the Barrian inhomogeneous universe model, and to appreciate it, we need to revisit one of the deepest mysteries in all of cosmology, the matter-antimatter asymmetry. We live in a universe made almost entirely of matter, but according to our best theories, the Big Bang should have created equal amounts of matter and antimatter. These two opposing kinds of particles would have immediately annihilated each other upon contact, leaving behind nothing but a sea of pure radiation. The fact that we exist at all is proof that this perfect symmetry was broken. Somehow, for every billion pairs of matter and antimatter particles that annihilated in the early universe, one single matter particle was left over. That one in a billion survivor is what all stars, planets, and people are made from. Now, this model asks a profound question. Was this survival process perfectly smooth and uniform across the entire cosmos? Or could it have been patchy? Imagine the universe cooling through the critical phase where matter and antimatter predominantly annihilate. It's possible that this process didn't happen with perfect consistency everywhere. Certain regions of space might have ended up with a slightly higher density of these leftover matter particles, these baryons, while adjacent regions might have been slightly more depleted. This wouldn't just be a minor variation, it would create a cosmic landscape of incredible contrast. You'd have dense continents of matter swimming in a much more diffuse ocean. When the nucleosynthesis window opened a few minutes later, these two different environments would have experienced completely different physical realities. In the high-density baryon regions, the sheer concentration of protons and neutrons would have made nuclear fusion incredibly efficient. Particles would have been bumping into each other constantly, rapidly building up deuterium and then helium, potentially using up all the available fuel very quickly. The fusion reactions might have even progressed further than in the standard model, perhaps creating trace amounts of elements slightly heavier than helium before the expanding universe put a stop to the party. Meanwhile, in the low-density regions, the opposite would be true. With particles more spread out, collisions would have been far less frequent. The crucial first step of forming deuterium would have been much more difficult, creating a severe bottleneck. The entire fusion chain would have been sluggish and inefficient. potentially leaving behind a much larger relative abundance of deuterium and far less helium than the Standard Model predicts. So, instead of one universal set of element abundances, the early cosmos would have been a patchwork quilt of different chemical outcomes. Over billions of years, through the process of galaxy formation and the mixing of interstellar gas, these vastly different primordial clouds would have stirred together, averaging out into the abundances we measure today on a large scale. But that averaging might not be perfect. The specific ratios of light elements we see, the exact amount of deuterium versus helium, or that stubborn lithium discrepancy, could be the blended signature of these wildly different starting conditions. It's a compelling solution because it doesn't require any new physics beyond the known mystery of baryogenesis itself. It simply suggests that the solution to that mystery might have created a more complex and textured infant universe than we ever imagined, and that the first elements are the enduring echo of that ancient, uneven struggle for existence. We've explored how gravity, exotic particles, and even the laws of physics themselves might have been different in the universe's first moments. Now, let's turn our attention to a more subtle but equally profound possibility, one that involves the ghostly neutrinos we met earlier and a strange quirk in their behavior. This is the lepton-flavored Big Bang Nucleosynthesis theory, a concept that hinges on a question of cosmic taste. In the particle physics world, flavor is the term used to distinguish between different types of a fundamental particle. For the charged leptons, that's the electron, the muon, and the tau particle, this is straightforward. They all have the same charge, but they have vastly different masses. An electron is light and familiar. A tau particle is over 3,000 times heavier. But neutrinos also come in three flavors: the electron neutrino, the muon neutrino, and the tau neutrino. And here's the critical point. In the hot, dense early universe, these different neutrino flavors might not have been created or distributed equally. The Standard Model of BBN assumes that all neutrino flavors were in perfect thermal equilibrium with the rest of the plasma, meaning they were all at the same temperature and interacting at the same rate. But this theory challenges that assumption. What if, due to their different masses and interaction cross-sections, the muon and tau neutrinos decoupled from the primordial soup slightly earlier than the electron neutrinos did? Or what if there was an initial, inherent asymmetry, a slight preference for one flavor over another imprinted from an even earlier time? This seemingly minor detail could have had a major domino effect, all centered on that crucial 1-second mark, neutron decoupling. Remember, the process that freezes the neutron-to-proton ratio relies entirely on the weak interactions mediated by the W and Z bosons, and these interactions are deeply intertwined with neutrinos. Specifically, the rate at which a neutron converts into a proton by emitting an electron and an antineutrino is sensitive to the density and energy of the antineutrinos already present in the environment. If the cosmos contained a different number of, say, muon antineutrinos compared to electron antineutrinos, it would subtly alter the pressure in this subatomic tug of war. A greater abundance of a specific flavor of antineutrino could have slightly impeded the conversion of protons into neutrons or vice versa, just as the door was slamming shut on the process. This would have left the universe with a final, frozen neutron-to-proton ratio that was different from the prediction of the Standard Model where all flavors are treated equally. Even a change of a fraction of a percent in this ratio would cascade directly into the nucleosynthesis process that follows. Fewer available neutrons would mean less helium-4 is produced. But the effect isn't linear. It would also change the delicate balance of the nuclear reaction chains that create and destroy deuterium and lithium. By carefully tuning this proposed neutrino flavor asymmetry, physicists can create models where the predicted abundance of lithium-7 drops significantly, potentially right into line with what we observe in those ancient stars, while still maintaining the successful predictions for helium and deuterium. It's a beautifully subtle mechanism. It doesn't require new particles or changing constants. It simply suggests that the neutrino population in the infant universe was more complex and varied than we've traditionally assumed, and that this rich tapestry of flavors left a faint but measurable signature on the very first atoms. Now, let's introduce one of the most enigmatic forces in the cosmos into our primordial story. We're all familiar with dark energy as the mysterious agent causing the universe's expansion to accelerate today. But what if this strange energy wasn't just a modern phenomenon? What if it also played a dramatic role in the universe's very first minutes? This brings us to our 11th theory, the early dark energy influence. To understand its potential impact, we need to revisit the single most important clock governing Big Bang nucleosynthesis, the expansion rate of the universe itself. The entire 3-minute window for creating the first elements is dictated by this relentless outward push. As the universe expands, it cools and the density of particles drops. The speed of this expansion is therefore the master timer for the fusion party. If the universe expands too quickly, the party ends early. Particles are spread thin before they can finish their intricate dance, leaving behind more unfinished products like deuterium and less of the end result, helium. If it expands too slowly, the party rages on for longer, allowing fusion to proceed more completely, consuming more deuterium and producing even more helium. The Standard Model assumes the expansion rate is governed primarily by the density of radiation and matter at that time. But this theory proposes an additional, transient player on the scene, a form of dark energy that was significant only in the universe's extreme youth. This isn't the subdued dark energy we see today, but a potent, early version that surged during the first few minutes before fading away to near insignificance. Imagine the early universe's expansion being driven not just by the energy of radiation, but also by this extra, exotic push from early dark energy. This additional energy density would have made the universe expand faster during the critical BBN epoch. The gravitational pull of any form of energy, even the repulsive kind associated with dark energy, contributes to the overall expansion dynamics described by Einstein's equations. A faster expansion means the temperature and density drop more rapidly. The neutron freeze-out happens a fraction of a second earlier, potentially altering the initial neutron-to-proton ratio. More importantly, the nucleosynthesis window slams shut sooner. The frantic chain reaction that builds helium from deuterium has less time to complete its work. This would leave a distinctive signature in the primordial abundances, an overproduction of deuterium because less of it gets used up in fusion, and an underproduction of helium-4 because the process is cut short before it can lock up all the available neutrons. Intriguingly, some observations of deuterium in the ancient universe suggest there might be slightly more of it than the standard BBN model predicts, which is exactly the kind of clue that makes this theory so compelling. Early dark energy could provide an elegant explanation. By tweaking the strength and duration of this early dark energy phase, cosmologists can adjust the model's expansion history to better match the observed elemental fingerprints. This idea is part of a broader class of models that consider dynamic dark energy, whose influence can change over cosmic history rather than remaining constant. It turns the mystery of the first elements into a potential probe for one of the greatest unknowns in modern physics, suggesting that the seeds of our accelerating universe today might have been sown in its very first moments, leaving a permanent record in the atoms forged during that explosive beginning. Now, let's venture into the shadowy realm of the cosmos's missing mass. For decades, astronomers have been confronted with overwhelming evidence that most of the matter in the universe is invisible, not made of atoms, but of something else entirely, dark matter. This mysterious substance outweighs all the stars, planets, and gas clouds put together by a factor of about 5 to 1. Its gravitational pull is what holds galaxies together and sculpts the large-scale structure of the universe. But we have no idea what it actually is. Among the many candidates proposed by physicists, one of the most compelling is a hypothetical particle known as the action. And our 12th theory proposes that these elusive actions, if they exist, could have been silent players in the drama of the first elements, subtly tweaking the cosmic recipe through their own unique behavior. The action was originally conceived not to solve a cosmological problem, but to fix a deep issue in particle physics known as the strong CP problem, a perplexing symmetry in the strong nuclear force that seems unnaturally perfect. The proposed solution was a new, very light, and very weakly interacting particle that would effectively clean up this mathematical inconsistency. It just so happened that this particle's properties also made it a perfect candidate for cold dark matter. Actions are theorized to be billions of times lighter than electrons, and crucially, they interact with ordinary matter only extremely rarely, flickering through the world like cosmic ghosts. But in the unimaginably dense environment of the very early universe, even these phantom particles could have been produced in staggering numbers and could have exerted a tangible influence. This theory, action-driven nucleosynthesis, explores two primary ways they might have left their mark. The first involves decay. Some models suggest that in the first few minutes, a population of these actions could have become unstable. They wouldn't last forever, and their preferred method of vanishing would be to decay into pairs of photons packets of electromagnetic energy. Now imagine the scene. The universe is a rapidly cooling plasma, its temperature dropping precisely on the schedule that allows for the careful freeze out of neutrons and the subsequent fusion into elements. Suddenly, these decaying actions begin to flood the environment with extra photons. This isn't just a light show, it's an injection of heat. This extra energy would have slightly reheated the primordial soup, delaying its cooling by a tiny but critical amount. This delay could have prolonged the period of neutron decoupling, allowing a few more neutrons to decay into protons before the process froze, or it could have extended the fusion window itself, giving the nuclear reactions a fraction of a second more to play out. Either way, the delicate balance of the final abundances would be shifted. The second potential mechanism is even more direct. The presence of a dense sea of actions could have influenced the weak interaction processes themselves. The decay of a free neutron into a proton is mediated by the weak force. If actions couple to this force in even a minuscule way, their sheer abundance could have acted as a background field that ever so slightly altered the probability of this decay happening. It might have sped it up or slowed it down. A change in the neutron decay rate during that crucial period between 1 second and 3 minutes would have a direct and powerful impact on the number of neutrons available to form helium. Fewer neutrons mean less helium, more neutrons mean more. The beauty of this action influence is its potential to solve the lithium problem without disrupting the otherwise successful predictions for deuterium and helium. By providing a subtle, external nudge to the system at just the right moment, these dark matter particles could account for the small discrepancy we observe. It's a profoundly elegant idea that the solution to the mystery of the universe's invisible majority might be written in the faint, ancient fingerprints of its very first visible atoms. The elements we see today could be the cosmic breadcrumbs leading us not only to the beginning of time but directly to the identity of dark matter itself. Now we journey into one of the most speculative and theoretically profound ideas on our list, a concept that emerges from the deepest ambitions of physics to unify all the fundamental forces of nature. This is the magnetic monopole catalysis theory, and it introduces a particle so exotic it has never been observed, yet its potential influence on the infant universe is staggering. To understand it, we first need to grasp what a magnetic monopole is. In our everyday experience, magnets always have two poles, a north and a south. You can break a bar magnet in half, but you'll always be left with two smaller magnets, each with its own north and south pole. A magnetic monopole would break this rule entirely. It would be a particle that is just a pure north magnetic pole or a pure south, a solitary point of magnetic charge. Their existence is a key prediction of grand unified theories, which attempt to describe how the electromagnetic, weak, and strong nuclear forces were all once a single, unified force in the ultra-high-energy environment of the very early universe. According to these theories, an unimaginably vast number of these monopoles should have been created in the first instance after the Big Bang, as the unified force began to splinter into the distinct forces we know today. Most of these primordial relics would have been rapidly diluted by the inflationary expansion of the universe, but it's possible a small, significant population persisted. Now, here's where their potential role in nucleosynthesis gets truly wild. These theorized monopoles aren't just curious magnetic oddities. They are predicted to possess a truly bizarre and powerful ability to catalyze proton decay. In the modern, cold universe, protons are incredibly stable. The experimental evidence suggests they might be practically immortal, with half-lives longer than the current age of the universe. But in the presence of a magnetic monopole, the rules change. The monopole's immense magnetic field could, in theory, provide a shortcut for a proton to spontaneously fall apart, decaying into lighter particles like a positron and a pion, and releasing a burst of energy in the process. This isn't just a minor decay, it's a catastrophic unraveling of stable matter. Now, transplant this concept back to the universe's first few minutes. The cosmos is a seething, dense broth of protons and neutrons. If even a modest number of these magnetic monopoles were zipping through this plasma, each one would act like a cosmic catalyst of destruction. As a monopole passed through, it wouldn't just nudge a few particles. Its mere presence could trigger a chain reaction, causing the protons and neutrons in its immediate vicinity to rapidly and violently decay. Each decay would release a significant amount of energy, creating localized, incredibly hot hotspots in the plasma. Think of it as a microscopic spark igniting a tiny firestorm of radiation and exotic particles. In these brief, intense maelstroms, the normal rules of Big Bang nucleosynthesis would be upended. The sudden injection of energy and the creation of unusual particle showers could open up entirely new and exotic nuclear reaction pathways. Instead of the orderly, step-by-step fusion chain of the standard model, you might get frantic, high-energy collisions that produce a different mix of elements. It could potentially create fleeting, unusual isotopes that aren't part of the standard BBN story. Or it could alter the delicate balance between the creation and destruction of the more common light elements like lithium. Perhaps the monopole-catalyzed decay of protons slightly reduced the overall baryon density in certain regions, or maybe the energy released provided the extra oomph needed to push certain rare fusion reactions over the energy barrier. While this idea remains one of the most hypothetical on our list, we have yet to find a single magnetic monopole. It represents a breathtaking synthesis of the largest and smallest scales of physics. It connects the quest for an ultimate theory of everything directly to the practical, observable problem of why the universe has the specific chemical composition it does. The first elements in this view might carry not just the signature of heat and expansion, but the faint, fading echo of a time when the cosmos was filled with the most peculiar and powerful relics of unification. These cosmic strings are theorized to have formed during a phase transition in the universe's earliest moments, a time when the fundamental forces were separating from their initial unified state, much like cracks forming in ice as water freezes. These weren't mere wrinkles in space, they were unimaginably dense, thinner than a proton yet stretching across the entire observable universe, each one possessing the mass of a mountain range packed into every inch of their length. Their gravitational influence was profound, warping the space around them into powerful gravitational wells. As the universe expanded, this network of strings would have evolved, vibrating and occasionally intersecting, creating loops that slowly decayed by radiating energy. Now place this chaotic, energetic network into the scene during Big Bang nucleosynthesis. The universe is a smooth, expanding plasma, but it is no longer perfectly uniform. The gravitational pull of these cosmic strings creates significant density fluctuations in their immediate vicinity. Clouds of primordial hydrogen and helium would have been drawn towards these ultra-dense defects, compressing the gas and creating regions of much higher pressure and temperature than the surrounding background. In these localized pockets, conditions become ideal for nuclear fusion to occur far more efficiently. It's like having a network of super-powered forges scattered throughout the cosmos, each one igniting a more intense and potentially longer-lasting burst of element creation. Near a cosmic string, the fusion chain reaction might not be cut short as quickly by the universe's overall expansion. This could allow the process to proceed further, potentially creating minute traces of elements slightly heavier than lithium, elements like beryllium or even boron, which are entirely absent from the predictions of the Standard Model. Furthermore, the decay of these string loops through gravitational radiation would have injected substantial energy into the plasma, again reheating local environments and potentially restarting or altering fusion processes that had already ceased elsewhere. The result wouldn't be a single, universal set of element abundances, but a cosmic patchwork. Some regions of space far from any strings would have the standard primordial mix. Other areas close to these defects would be enriched with a slightly different chemical signature, perhaps with less lithium due to more efficient fusion, or with exotic, rare isotopes we wouldn't expect to find. Over billions of years, as the universe evolved and galaxies formed from this unevenly mixed gas, these variations would have been mostly homogenized, but their faint imprint might still be detectable as subtle anomalies in the elemental compositions of the very oldest stars. The search for such anomalies is an active area of research, as finding them could provide the first indirect evidence for these fantastical structures woven into the very fabric of space-time. Imagine if the familiar three dimensions of space were not the whole story. We live our lives moving forward and backward, left and right, up and down a comfortable three-dimensional reality. But many of our most promising theories for unifying gravity with quantum mechanics, particularly string theory, posit that the universe actually has more dimensions, perhaps 10 or 11 in total. These extra dimensions are thought to be incredibly tiny, curled up on a scale a billion times smaller than an atom, which is why we don't perceive them in our everyday lives. But in the extreme energy and density of the Big Bang, all bets are off. This theory suggests that in that first second, the universe was so small and so hot that these extra dimensions were not curled up and hidden. They were open for business, playing a direct and active role in the physics of creation. Gravity, which we experience as the weakest of the four fundamental forces, is thought to be so feeble in our three-dimensional world because most of its strength is actually leaking away or diluting into these extra dimensions. But in the first instance of the universe, when all dimensions were compact and on an equal footing, gravity would have been immensely more powerful. It would have been a force to rival the strong and weak nuclear interactions. This radical shift in the hierarchy of forces would have had a profound and immediate impact on the expansion rate of the cosmos. A dramatically stronger gravitational pull in those first moments could have caused the universe to expand at a vastly different pace, either slowing it down or speeding it up in ways the Standard Model doesn't account for. That change in expansion is the master clock for everything that follows. A faster expansion would have slammed the door on nucleosynthesis earlier, leaving more deuterium unprocessed and less helium formed. A slower, more ponderous expansion could have extended the fusion window, allowing more time to build heavier elements and consume more of the available hydrogen. But the influence might not stop there. the nuclear forces themselves, which govern how protons and neutrons stick together, could have also been subtly different if they were operating in a space with more than 3 dimensions. The strength of the strong nuclear force, the very glue that holds atomic nuclei together, might have been modulated by the geometry of these hidden dimensions. A slight change in its strength would have monumental consequences. A stronger nuclear glue would make deuterium bind more easily, turbocharging the entire fusion chain and potentially producing more helium. A weaker force would make it harder for any nuclei to form at all, creating a massive bottleneck. The potential outcomes are as varied as the possible geometries of the extra dimensions themselves. This model transforms the problem of the light element abundances from a question of particle physics into a question of cosmic geometry. The specific amounts of hydrogen, helium, and lithium we see today could be a fossilized record, a permanent clue, telling us what the true, full-dimensional shape of the universe was like in its very first heartbeat. It suggests that by looking at the oldest atoms, we might not just be seeing the aftermath of a nuclear reaction, but actually reading the signature of a higher dimensional reality imprinted onto our 3-dimensional world. But to push the boundaries of cosmic weirdness even further, let's consider a substance so bizarre it defies our conventional understanding of matter itself. This brings us to the quark nugget hypothesis, a theory that proposes the existence of incredibly dense, stable lumps of pure quark matter that might still be drifting through the universe today, potentially forming the very essence of dark matter. To grasp this, we need to revisit the quark gluon plasma, that primordial soup of free particles that existed before protons and neutrons formed. The standard story is that when the universe cooled, all these quarks dutifully bound together in groups of 3 to form the protons and neutrons we know. But what if that transition wasn't completely clean? What if, in some regions, a vast number of up, down, and strange quarks managed to clump together into much larger macroscopic blobs? These wouldn't be individual particles, they'd be city-sized or even mountain-sized chunks of ultra-dense quark matter, often called strangelets or quark nuggets. The strange in the name is key. Ordinary matter is made of up and down quarks, but there's a third flavor, the strange quark. Theory suggests that under immense pressure, matter might actually achieve a more stable state by incorporating roughly equal numbers of up, down, and strange quarks. This strange matter could be the most stable form of matter in the entire universe, more stable than even an iron nucleus. If such chunks formed in the first microseconds after the Big Bang, they wouldn't have decayed. They would have persisted, frozen relics of the universe's most extreme conditions. Now, how could these hypothetical quark nuggets influence the creation of the first elements? Imagine these incredibly dense objects peppering the primordial plasma during the nucleosynthesis epoch. Each nugget would be a gravitational anchor, a point of immense density. The protons and neutrons swirling in the plasma would be drawn towards them, creating a localized cloud of higher baryon density in their immediate vicinity. In these dense clouds, the nuclear fusion reactions would proceed much more vigorously and efficiently than in the average regions of space. It's like having countless microscopic factories scattered throughout the cosmos, each one running a hotter, faster version of the standard process. This could significantly alter the final mix of elements produced in those zones. Perhaps near a quark nugget, fusion was so efficient that it burned up nearly all the available deuterium, or maybe it allowed for the production of trace amounts of elements that are otherwise impossible to make in the standard model. When you average the output of these hyperactive zones with the more sedate output from the regions far from any nuggets, you might arrive at a universal abundance that matches our observations, including that perplexing lithium shortfall. The implications of this idea are staggering. These quark nuggets, if they exist, would be incredibly massive yet incredibly compact. A nugget the size of a grain of sand could weigh as much as a mountain. Billions of them could be drifting undetected through our galaxy right now. Because they are made of quarks, not atoms, they wouldn't emit or reflect light. They would be completely dark and virtually invisible. This makes them a prime candidate for the mysterious dark matter that governs the dynamics of every galaxy. In this breathtaking synthesis, the quark nugget hypothesis doesn't just offer a solution to a minor anomaly in the cosmic recipe. It proposes that the very same exotic objects that subtly guided the formation of the first visible atoms are also the invisible scaffolding of the entire universe, the hidden mass that has shaped the cosmos from its very first moments to the present day. But what if the story of the elements doesn't actually begin with our Big Bang? We've been exploring how the conditions within the first few minutes shaped the cosmic recipe, but this next idea turns that entire timeline on its head. This is the pre-Big Bang nucleosynthesis scenario, a theory that suggests our universe inherited some of its chemical ingredients from a previous cosmic cycle. Imagine our Big Bang wasn't an absolute beginning, but rather a dramatic transition from a prior state of existence, a cosmic rebirth. In such a model, the universe might have undergone a period of contraction, often called the Big Crunch, before bouncing back into the expansion we see today. During that previous phase of existence, that prior universe could have had its own stars, its own galaxies, and its own periods of nucleosynthesis. As it contracted towards its final moments, those stars would have been torn apart in a cataclysm of unimaginable force, forging and scattering their elemental ashes into a superheated, ultra-dense plasma. Then, when the Big Bang occurred, or the Big Bounce, that pre-existing material wouldn't have just vanished. It would have been reprocessed, diluted, and mixed into the seething inferno of the new universe's birth. The primordial hydrogen and helium we attribute to the first 3 minutes might not be entirely pristine. They could contain a faint but significant contamination, a relic abundance of elements forged in the furnaces of a world that existed before our own. This isn't just about adding a few extra atoms, it challenges the very definition of primordial. The most sensitive test of standard Big Bang nucleosynthesis is the ratio of certain light elements, particularly the amount of deuterium and lithium. These abundances are like a cosmic fingerprint, uniquely tied to the specific density and temperature profile of our universe's first minutes. If a supply of pre-existing helium, deuterium, or even trace amounts of lithium were already present when our Big Bang began, it would completely distort that fingerprint. The careful calculations that so perfectly match observation would be thrown into disarray because the starting conditions for the nuclear reactions would no longer be a clean slate of pure protons and neutrons. Finding conclusive evidence for this is one of the greatest challenges in cosmology. How do you distinguish an atom forged in our Big Bang from one that is a billion-year-old relic from a previous cosmic cycle? One potential signature might be found in the detailed isotopic ratios of the very oldest stars. If some of their material came from a previous universe, the specific proportions of different lithium or helium isotopes might show a pattern that cannot be explained by any process that occurred within our own cosmic timeline. It's a faint hope, but it demonstrates how the mystery of the first light elements connects to the most profound questions we can ask about existence itself. Are we the first universe or merely one in an infinite cycle? The answer might be hiding in plain sight, encoded in the ancient atoms that make up everything we are. The timeline of the early universe is often presented as a smooth, inevitable cooling from an infinite heat. But what if that cooling wasn't quite so straightforward? Our 18th theory invites us to reconsider the universe's thermal history, questioning whether its temperature dropped on a simple, predictable curve or if it was punctuated by dramatic events that reset the cosmic clock. This isn't a minor detail. The exact temperature profile of the infant cosmos is the master conductor for the entire symphony of creation, dictating the precise moment the music of nuclear fusion could begin and end. Think of it like baking a cake. The Standard Model gives us a very specific recipe. Preheat the universe to an unimaginable temperature, then let it cool for exactly 1 second before adding the neutrons and protons. But this theory asks, what if the oven door was opened and closed a few times during that first second? What if there was a sudden burst of heat that briefly reheated everything? Even a tiny fluctuation in the thermal timeline would have a profound impact on the most crucial initial condition for nucleosynthesis, the neutron-to-proton ratio. This ratio is set at the moment of neutron decoupling, that pivotal 1 second mark when the universe cools enough that protons and neutrons stop interconverting. The temperature at that exact instant determines how many neutrons are available to be the building blocks for everything heavier than hydrogen. A universe that cools just a fraction of a second faster would have a higher neutron count frozen in, leading to more helium. A universe that holds its heat a moment longer would see more neutrons decay away, resulting in less helium and more leftover hydrogen. One of the most compelling ways this could have happened involves the end of the inflationary epoch. Most models of inflation conclude with a period called reheating, where the immense energy stored in the inflationary field is dumped back into the universe, refilling it with a hot, dense plasma of particles and effectively restarting the Standard Big Bang timeline. The details of this reheating process are still highly theoretical. Was it instantaneous? Was it a gradual trickle? The answer matters immensely. A violent, sudden reheating event could create powerful shock waves and temperature inhomogeneities throughout the plasma. A more gentle, prolonged release of energy might maintain a more uniform temperature, but could slightly extend the time before the final cooling begins. Either scenario would mean the universe's time zero for nucleosynthesis calculations isn't a clean, well-defined point. The neutron freeze-out wouldn't happen at a universally uniform temperature, but could vary slightly from region to region based on the local thermal history from reheating. This variability offers a powerful lever to adjust the predictions of the Standard Model. By carefully modeling different reheating scenarios and their effect on the cooling rate, cosmologists can subtly change the neutron-to-proton ratio at freeze-out. This, in turn, cascades through every calculation that follows. A slight adjustment here can lower the predicted abundance of lithium-7 without messing up the successful predictions for helium and deuterium. It provides a mechanism to explain the observed anomalies without invoking new particles or forces, simply by refining our understanding of how the universe emerged from its inflationary phase. The thermal history of the universe is its biography, written in degrees and seconds. By questioning the assumptions of that biography, we might find that the key to the lithium problem wasn't in the nuclear physics of the first 3 minutes, but in the thermodynamic events of the very first second. Now, let's revisit those ghostly cosmic messengers, the neutrinos, but this time we'll focus on one of their most intriguing and experimentally verified behaviors, their ability to change identity. This brings us to our 19th theory, which hinges on the fascinating phenomenon known as neutrino oscillation. We've already seen how the sheer number and flavor of neutrinos could influence the early universe, but this idea goes a step further. It proposes that the very act of a neutrino transforming from one type into another could have had a direct and measurable impact on the recipe for the first elements. To appreciate this, we need to understand what oscillation means. Neutrinos are famously elusive, but they're also surprisingly fickle. A neutrino born as an electron neutrino doesn't necessarily stay that way. As it travels through space, it has a probability of spontaneously transforming into a muon neutrino or a tau neutrino, and then later changing back. This isn't some random fluctuation, it's a fundamental quantum mechanical property that proves neutrinos have mass, however tiny. Their journey is a constant probabilistic dance between the three flavors. In the calm emptiness of today's universe, this dance is a solitary one. but transplant this behavior back to the incredibly dense environment of the first second after the Big Bang, and the implications become profound. The weak interaction processes that set the neutron-to-proton ratio, those critical conversions that freeze out at the 1-second mark, are exquisitely sensitive to the specific type of neutrino involved. An electron neutrino interacts differently with matter than a muon neutrino, so the rate at which a proton converts into a neutron or vice versa depends on the flavor of the neutrino that's mediating the reaction. The standard model of Big Bang nucleosynthesis makes a key assumption that all neutrino flavors are in perfect equilibrium and that their populations are static. But what if they weren't? Neutrino oscillation means the populations were dynamic. The fraction of the neutrino C that was electron flavor at any given microsecond was constantly shifting as these particles danced between their identities. If oscillations were happening rapidly during that crucial 1-second window when the neutron-to-proton ratio was being determined, they would have effectively changed the interaction rates on the fly. Imagine the weak interaction processes as a series of doors. An electron neutrino can open some doors very easily, while a muon neutrino finds them more difficult. Now imagine the doormen at these doors are constantly swapping places. The flow of particles through the doors would become unpredictable. A region of space might, for a brief moment, have a higher effective density of electron neutrinos, speeding up certain reactions. An instant later, that density could drop, slowing them down. This dynamic, oscillating environment could have slightly altered the final balance between neutrons and protons frozen at decoupling. Even a minuscule shift, a fraction of a percent, would be enough to change the predicted amount of helium-4 by a significant margin. This provides a remarkably elegant and subtle mechanism to fine-tune the predictions of the Standard Model. By incorporating the known physics of neutrino oscillation into the complex equations of the early universe, cosmologists have a new set of dials to turn. They can adjust the model to account for the observed helium abundance with even greater precision, potentially resolving tiny discrepancies without needing to invoke any exotic new particles or forces. It demonstrates that the answers to our biggest cosmic questions aren't always found in the grand and the strange, but sometimes in the subtle, quantum-scale dance of the universe's most abundant particles. Now, let's introduce a force into the primordial soup that we can actually feel in our everyday world, but one whose potential power in the universe's infancy is truly staggering: magnetism. This brings us to our 20th theory, which asks whether the universe's first elements were shaped not just by heat and gravity, but by immense primordial magnetic fields. We're all familiar with magnets, but we usually think of them as a property of certain metals or planets. The idea that the entire newborn cosmos could have been crisscrossed by powerful magnetic fields from its very first instance might seem far-fetched, but it's a serious proposition with profound implications for the story of creation. To understand how a magnetic field could influence nuclear fusion, we need to remember that the key players in Big Bang nucleosynthesis, protons and the nuclei they form, are all positively charged. And charged particles behave in a very specific way when placed in a magnetic field. Their paths become curved. Instead of moving in straight lines, they are forced to spiral along the magnetic field lines like beads on an invisible wire. In the frenzied, hot plasma of the early universe, this would have had two major effects. First, it would have guided the particles, effectively funneling them and increasing the likelihood of collisions in regions where the field lines converged. Second, and perhaps more importantly, it would have confined them. A strong enough magnetic field can act as a cage, preventing particles from wandering away and keeping them in a dense, high-pressure environment ideal for nuclear reactions. This isn't just about making fusion happen a bit faster. It could have fundamentally altered the probabilities of certain rare reactions. Let's take the specific case of lithium-7, the element whose predicted abundance has been such a persistent problem. Lithium-7 is primarily created through a very delicate and slow process, the radioactive decay of beryllium-7, which itself is formed when a helium-4 nucleus fuses with a helium-3 nucleus. This is a rare collision to begin with. Now, imagine a universe threaded with powerful magnetic fields. These fields could have corralled the charged helium nuclei, increasing their density in localized zones and dramatically raising the odds of these unlikely helium-helium collisions taking place. If this happened, it could have led to a much higher production of beryllium-7 and thus more lithium-7 than the Standard Model predicts. This seems like it would make the lithium problem worse, not better. But the story doesn't end there. These same magnetic fields could have also influenced the destruction of lithium. Lithium nuclei are themselves charged and would also be guided by the field. This might have made them more likely to collide with other particles, including free protons, leading to reactions that break them apart. So, a primordial magnetic field could be a double-edged sword. It might boost the creation of lithium in one channel while simultaneously enhancing its destruction in another. The final abundance we would see today is the net result of this push and pull. By carefully modeling the proposed strength and structure of these early fields, physicists can explore whether this magnetic influence could bring the predicted amount of lithium into closer alignment with what we actually observe. The field's strength is a critical variable here. A magnetic field 1 billion times stronger than any we can create in labs today would have been a dominant force in the microscopic physics of the early universe, while a weaker one might have had only a negligible effect. The challenge, of course, is that these fields would have left no permanent direct fossil for us to find. Their energy would have been diluted to near nothing by the universe's expansion. However, they might have left an indirect signature. The motions they imparted on the plasma could have created faint, twisting patterns in the cosmic microwave background radiation, the afterglow of the Big Bang. While we haven't definitively found this signature yet, the search continues, making the mystery of the first elements a potential key to unlocking another hidden chapter of the cosmos's magnetic history. Up until now, we've largely considered the early universe as a place where everything happened in perfect, predictable balance. A smooth, thermalized soup where particles had all the time and proximity they needed to reach equilibrium. But what if that assumption of perfect balance is the very thing that's led us astray? This brings us to a particularly subtle but powerful idea, the non-equilibrium thermodynamics approach. It suggests that the frantic pace of the universe's infancy might have prevented certain key nuclear reactions from ever reaching a settled state, leaving behind a chemical fingerprint that a perfectly balanced model could never explain. To understand this, imagine trying to bake a cake while the oven temperature is plummeting and the kitchen is expanding at nearly the speed of light. That's the challenge facing particles during Big Bang nucleosynthesis. The Standard Model assumes that the most important nuclear reactions manage to stay in equilibrium, meaning the rate at which nuclei were forming was perfectly balanced by the rate at which they were being broken apart by high-energy photons, right up until the universe cooled so much that the reactions simply froze in place. But this theory proposes that for some delicate reactions, equilibrium was never truly achieved. The expansion was simply too fast, the window of opportunity too brief. The most crucial candidate for this non-equilibrium effect involves the very first and most fragile step in the entire chain, the formation of deuterium. Creating a deuterium nucleus is a precarious business. It's only very weakly bound, so it's easily shattered back into a proton and a neutron by the intense bath of radiation filling the young cosmos. In the standard picture, there's a precise moment called the deuterium bottleneck, where the universe finally cools enough that these destructive photons can no longer break deuterium apart faster than it forms. Only then does the fusion floodgate open. But what if the expansion was so rapid that it effectively swept the universe through this critical temperature point faster than the deuterium-forming reactions could adjust? The particles wouldn't have had time to find their new equilibrium. The result would be a lingering underproduction of deuterium at the very moment the chain reaction is supposed to kick into high gear. With less deuterium available as fuel, the subsequent steps that build helium would be starved, potentially leading to a lower final abundance of helium-4 than the Standard Model predicts. Conversely, if the expansion was just a touch slower in certain regions, allowing the deuterium abundance to briefly overshoot its equilibrium value, it could have turbocharged the fusion process, creating more helium. This non-equilibrium state wouldn't just affect the amounts of the main elements, it could be the key to the lithium problem. Lithium-7 is not forged directly in the fire. It's the decay product of the unstable isotope beryllium-7, which itself is created through a rare and slow reaction between two helium nuclei. This is precisely the kind of delicate process that will be highly sensitive to the universe's frantic expansion rate. If conditions never settled into a steady state, the reaction forming beryllium-7 might never have reached its full potential, leading to a chronic underproduction of its lithium daughter. The non-equilibrium approach provides a dynamic framework where the frantic, real-time physics of an explosively growing cosmos, not just its average conditions, directly writes the final elemental recipe. It suggests that the fossil record of the light elements is not a snapshot of a serene, balanced event, but a high-speed photograph of a system perpetually playing catch-up, forever frozen in a state of becoming. Now we journey even deeper into the speculative realms of particle physics to meet a hypothetical character whose very existence could have thrown the universe's first moments into chaos. This is the gravitino, and its potential impact on the cosmic recipe forms our 22nd theory. To understand the gravitino, we must first recall the concept of supersymmetry, which proposes that every fundamental particle has a heavier superpartner. The graviton is the hypothetical particle that mediates the force of gravity in quantum theories. If supersymmetry is real, then the graviton must have a partner too, the gravitino. It's a particle that marries the properties of a graviton with those of a supersymmetric particle, making it incredibly massive and crucially unstable. In the extreme energy of the early universe, these gravitinos would have been produced in abundance. But as the cosmos expanded and cooled, they would have become a ticking time bomb. Their preferred method of decay is to break down into a lighter, more stable supersymmetric particle and emit a tremendously high-energy photon in the process. Now place this event within the delicate timeline of Big Bang nucleosynthesis. The universe is a precisely cooling plasma. The temperature is dropping on a perfect curve to allow for the freeze out of neutrons and the subsequent 3-minute window of fusion. Suddenly, a population of these gravitinos begins to decay. Each decay is a miniature bomb going off, flooding the environment with a blast of high-energy radiation. This isn't just a light show, it's a catastrophic injection of heat into a system that is critically dependent on its cooling schedule. These high-energy photons would have had two potential disruptive effects. The first is direct destruction. The photons produced in gravitino decay would be so energetic they could blast apart any light nuclei that had already managed to form. Imagine the first fragile deuterium nuclei beginning to appear, only to be immediately shattered back into their constituent protons and neutrons by this sudden barrage of radiation. It would be like a hailstorm tearing apart the first buds of spring, creating a severe bottleneck that could delay the entire nucleosynthesis process. The second, more subtle effect is on the plasma's temperature itself. This sudden, widespread energy injection would effectively reheat the universe. Just as the plasma was cooling to the perfect temperature for nuclear fusion to begin, this event could pump energy back into it, delaying the critical cooling threshold. This would prolong the period where free neutrons are decaying away, potentially altering the final neutron-to-proton ratio that is so vital for determining how much helium can be formed. A longer delay means fewer neutrons available when fusion finally does get underway, which would result in less helium and more leftover hydrogen and deuterium. The precise impact depends entirely on the gravitino's mass and its lifetime, how long it takes to decay after the Big Bang. If it decayed very early during the first second, the disruption might have been absorbed and the universe could have quickly returned to its thermal timeline. But if its decay happened right in the middle of the nucleosynthesis window between 1 and 3 minutes, it could have completely derailed the process. The beauty of this theory is that it provides a mechanism to significantly alter the predicted elemental abundances. By tuning the properties of the gravitino, physicists can create models that might explain, for instance, the lithium problem by showing how this disruptive event could have preferentially destroyed certain isotopes or altered the reaction pathways. The gravitino thus represents a double threat, a particle whose creation in the hot early universe is almost inevitable in certain theories, and whose decay could unravel the careful work of the first 3 minutes, leaving behind a cosmic chemical record that deviates from our simplest predictions in ways we are only beginning to understand. But what if our entire universe is just one slice of a much larger, higher dimensional reality? This idea might sound like the plot of a science fiction novel, but it's a serious proposal from string theory known as the brane world cosmology, and it forms the basis of our 23rd theory. Imagine our three-dimensional universe not as an isolated bubble, but as a membrane, a brane for short, floating within a higher dimensional space often called the bulk. In this mind-bending picture, the particles and forces we know and love, like electrons and photons, are stuck to our brane, unable to venture into the higher dimensions. But gravity is different. Gravity, in many of these models, is a weak force because it's not confined to our brane. It can spread out or leak into the extra dimensions. This leakage explains why gravity is so astronomically weaker than the other fundamental forces. But in the incredibly dense, hot environment of the early universe, this feature wouldn't just be a curious fact. It would be the master controller of the entire expansion rate, and therefore the architect of the first elements. To grasp its potential impact, we need to focus on that master clock again, the Hubble expansion rate. This rate dictates how quickly the universe grows and cools, and it's this cooling that determines the precise timing of neutron decoupling and the duration of the nucleosynthesis window. In the Standard model, this expansion rate is calculated based on the density of all the energy sources confined to our three-dimensional universe: radiation, matter, and so on. But in a brane world scenario, the equation changes dramatically. The gravitational field leaking into the extra dimensions adds new terms to the equations that govern cosmic expansion. In the first few minutes, when the universe was immensely dense, this effect would have been utterly profound. The leakage of gravity would have effectively weakened its pull within our brane, causing the universe to expand at a much faster rate than in the Standard model. It's as if the brakes on the universe's expansion were partially released. Now, let's follow the domino effect of this faster expansion. A universe that expands more rapidly cools more quickly. This means the critical moment of neutron decoupling, that 1 second mark when the neutron-to-proton ratio is frozen, would happen earlier. With less time for neutrons to decay into protons, the frozen ratio would contain a slightly higher fraction of neutrons. On the surface, that might suggest more fuel for building helium. However, the faster expansion has a second, competing effect. It drastically shortens the precious window for nuclear fusion itself. Just a few minutes later, when protons and neutrons should be frantically pairing up, the rapid expansion would have already diluted the particle density so much that collisions become far less frequent. The entire fusion chain reaction would be starved and cut short. The net result of these two opposing influences is a cosmic recipe with a distinct signature. Models suggest that a brane world scenario would typically lead to a higher abundance of deuterium, because the process is halted before much of it can be used up to form helium, and a lower abundance of helium-4 itself, because while there might be more neutrons available, there simply isn't enough time to efficiently incorporate them all into nuclei. This creates a tantalizing possibility. The precise amounts of deuterium and helium we observe in the ancient universe could act as a probe, not just of particle physics, but of the very geometry of reality itself. A confirmed discrepancy that aligns with brane world predictions would be powerful, albeit indirect, evidence that we are indeed living on a membrane in a reality with more dimensions than we can perceive, and that the first atoms carry the permanent imprint of that higher dimensional architecture. But to truly question the foundations of our reality, we must examine the very numbers we consider constant, the immutable parameters that underpin all of physics. This brings us to a theory that is as profound as it is controversial: the idea that the fine structure constant, a fundamental measure of the strength of electromagnetic interactions, was not always the same. Known by the Greek letter alpha, this constant is a pure number that dictates how tightly electrons are bound to atoms, how light interacts with matter, and crucially for our story, how atomic nuclei interact with one another. Its value is approximately 1/137th, and we have always assumed it is a fixed pillar of the cosmos. But what if, in the furious heat of the first 3 minutes, alpha was different? The fine structure constant is the key that sets the energy scale for all of chemistry and nuclear physics. Its value directly influences the strength of the electromagnetic force, which is the force responsible for the repulsion between positively charged protons. This repulsion, known as the Coulomb barrier, is the primary obstacle that protons must overcome to get close enough for the strong nuclear force to bind them together into nuclei. In the standard model of Big Bang Nucleosynthesis, this barrier has a fixed known strength. But if alpha were larger in the early universe, the electromagnetic force would have been stronger. This would have raised the Coulomb barrier even higher, making it significantly more difficult for protons to fuse. The formation of deuterium, that all-important first step, would have faced a much more difficult challenge. The entire fusion chain would have been severely bottlenecked, resulting in far less helium production and leaving a much larger residual abundance of deuterium and hydrogen. Conversely, if the fine structure constant were slightly smaller during those first minutes, the electromagnetic force would have been weaker. The Coulomb barrier would have been lower, almost like turning down the voltage on an electric fence. Protons and atomic nuclei would have found it easier to approach each other and fuse. The nuclear reactions would have proceeded with greater ease and efficiency, potentially consuming more of the available deuterium and producing more helium-4 than the standard model allows. The entire process might have even been able to produce trace amounts of heavier elements like beryllium or boron, which are completely absent from standard predictions. This potential variability offers a remarkably elegant lever to pull when trying to solve the persistent lithium problem. The creation and destruction of lithium-7 involve a complex web of nuclear reactions, each with its own sensitivity to the strength of the electromagnetic force. A carefully chosen variation in alpha could tweak the probabilities of these competing reactions, perhaps suppressing the production channel for lithium-7 just enough to bring the theoretical predictions into perfect alignment with the stubbornly lower amounts we observe in the ancient stars of our galaxy. The beauty of this idea is that it doesn't require inventing new particles or forces. It simply suggests that one of the most fundamental numbers in nature might have been settling into its modern value during the universe's fiery birth. The million-dollar question, of course, is how we could possibly test such a radical idea. The answer lies in looking back in time, using the universe itself as a laboratory. Astronomers do this by studying the light from the most distant quasars, which are incredibly bright galactic cores. As this ancient light travels for billions of years to reach our telescopes, it passes through immense clouds of interstellar gas. Atoms within these clouds absorb light at very specific wavelengths, which are directly determined by the value of the fine structure constant. By meticulously analyzing these absorption lines, scientists can effectively measure alpha in the distant past. Some of these studies have tentatively suggested that alpha might have been ever so slightly different billions of years ago, although the results remain hotly debated within the scientific community. If confirmed, it would mean the laws of physics are not static but dynamic. The fossil record of the light elements would then become more than just a relic of a nuclear event. It would be a permanent testament to a time when the very constants of nature were still evolving, a dramatic echo from an era when the universe was literally writing its own rules. But to truly challenge our understanding of the universe's most elusive particles, we must now introduce a ghost even more phantom-like than the ones we've met before. This brings us to a theory that operates in the shadows of the Standard Model, proposing the existence of a neutrino that doesn't even play by the usual rules. Welcome to the compelling mystery of the sterile neutrino mixing model. We're familiar with the three active neutrinos, the electron, muon, and tau varieties that flicker through the world, occasionally bumping into matter via the weak nuclear force. But what if there's a fourth? A sterile neutrino, as the name implies, would be a true cosmic recluse. It would feel only gravity, completely ignoring the weak force that allows its active cousins to interact. This makes it incredibly difficult to detect, but its potential influence on the early universe could have been profound, all thanks to a strange quantum behavior known as mixing. Imagine the neutrino population in that first second as a vast ocean. The active neutrinos are like the surface waves, constantly interacting with the plasma and influencing the crucial processes that set the neutron-to-proton ratio. But beneath the surface, there could be deeper, hidden currents, the sterile neutrinos. According to this theory, these two populations weren't entirely separate. Through a quantum mechanical process, an active neutrino could spontaneously oscillate or transform into a sterile one, and vice versa. This isn't a physical conversion, it's a shifting of identity, a sharing of properties across the quantum divide. When an active neutrino oscillates into its sterile counterpart, it effectively vanishes from the active sea. It's no longer participating in the weak interaction processes that are so critical for maintaining the balance between protons and neutrons. Now consider the immense scale. The early universe contained a staggering number of neutrinos, billions for every proton or neutron. Even a small probability of this active-to-sterile oscillation would have siphoned off a significant fraction of the active neutrino population at the most critical moment. This loss would have had a direct and powerful impact on the weak interaction rates that govern neutron decoupling. Fewer active electron antineutrinos, for instance, would mean fewer interactions where a proton absorbs an electron and an antineutrino to become a neutron. This would subtly tilt the balance in favor of protons, leaving the universe with a lower final neutron-to-proton ratio when the process froze at the 1-second mark. This shift, though it might sound minor, is everything in the high-stakes world of Big Bang nucleosynthesis. Fewer available neutrons means less fuel for building helium. The entire fusion chain that follows would be starved, resulting in a lower predicted abundance of helium-4. This is a key strength of the theory, as some astronomical observations have occasionally suggested the primordial helium abundance might be a touch lower than the strictest Standard Model predictions. By carefully tuning the proposed mass and mixing angle of the sterile neutrino, physicists can adjust how many active neutrinos were effectively hidden away, fine-tuning the model's helium output to potentially achieve a better match with what we observe. The sterile neutrino thus acts as a hidden reservoir, a shadow population that subtly drains energy and particles from the active sector, leaving a permanent, measurable imprint on the universe's very first and most enduring chemical signature. We've journeyed through theories that tweak densities, introduce new particles, and even suggest extra dimensions. But to approach the ultimate frontier of this mystery, we must venture to a time before time itself had any meaning, to an era where the very concepts of space and temperature break down. This brings us to a realm of pure speculation, yet one grounded in our most ambitious attempts to unify physics: the potential influence of quantum gravity on the first moments of creation. Our current understanding of the universe is split between two brilliant but incompatible rulebooks. We have Einstein's general relativity, which masterfully describes the gravity of planets, stars, and the cosmos itself. And we have quantum mechanics, which with stunning accuracy governs the bizarre, probabilistic world of atoms and subatomic particles. For decades, physicists have struggled to combine these two theories into a single, unified framework of quantum gravity, a theory of everything. The leading candidates, like string theory and loop quantum cosmology, suggest that near the moment of the Big Bang, when the entire universe was compressed into a space smaller than an atom, the quantum nature of gravity would have been the dominant force. This period, known as the Planck epoch, is a complete mystery. Our laws of physics simply cannot describe it. But what if the echoes of that unknowable epoch reverberated forward in time, subtly influencing the universe once it became large enough for our physics to work? This theory proposes exactly that. It suggests that quantum gravity effects in the first fractions of a second could have set the initial conditions for the entire cosmos in a way that standard models don't account for, and that this unique fingerprint might be preserved in the abundances of the light elements. One of the most developed ideas here comes from loop quantum cosmology, an approach that applies the principles of loop quantum gravity to the universe as a whole. This model offers a breathtaking alternative to the classical Big Bang singularity. Instead of a point of infinite density, it proposes a big bounce. In this scenario, our universe is not the absolute beginning but was born from the collapse of a previous cosmic phase. As that prior universe contracted, instead of crushing into a singularity, the repulsive forces of quantum geometry became so powerful that they caused a rebound, launching the expansion we see today. This bounce isn't just a philosophical alternative, it has tangible physical consequences. The model predicts that the pre-Big Bang phase would have left behind a specific kind of quantum memory, an imprint on the new universe. This could have manifested as subtle corrections to the very equations that describe how the universe expanded and cooled in its earliest moments. For Big Bang nucleosynthesis, the most significant effect would be on the expansion rate itself, that master clock we've returned to again and again. A quantum gravity-driven expansion history might have been slightly different, perhaps a bit slower or faster at critical junctures, which would have directly altered the neutron freeze-out time and the duration of the fusion window. Furthermore, these quantum gravity effects could have introduced entirely new terms into the thermodynamic playbook of the early cosmos. They might have modified the effective equation of state of the primordial plasma, the relationship between its pressure and density. Imagine the universe's first matter not as a perfect fluid, but as a substance with a fundamentally different character, its properties nuanced by the underlying quantum structure of spacetime. This could have changed how quickly sound waves traveled through the plasma or how efficiently energy was distributed, potentially creating those tiny inhomogeneities that other theories propose, but from a much deeper, more fundamental origin. The beautiful and frustrating thing about this idea is its testability. The predictions of loop quantum cosmology for the light elements are not just vague hand-waving, they are precise and quantifiable. By incorporating these quantum corrections into the nucleosynthesis equations, physicists can calculate new predicted abundances for helium, deuterium, and lithium. The goal is to see if these new numbers provide a better fit to the observational data, particularly for that stubborn lithium problem. Finding such a match would be revolutionary. It would mean that the fossil record of the first elements is not just a relic of nuclear processes, but a direct messenger from the Planck epoch, carrying clues about the quantum nature of spacetime itself. It would be our first empirical window into a realm that has until now been purely the domain of mathematical speculation. This brings us to a theory that connects two of the grandest puzzles in all of cosmology: the origin of the universe's material content and the specific recipe of its first atoms. We call this the Erfolg-Dyn baryogenesis connection, a concept that proposes the very mechanism that gave us a universe of matter might have also directly tampered with the ingredients for the first elements. To appreciate this elegant link, we first need to understand the monumental problem it aims to solve. Why does anything exist at all? Our best theories indicate the Big Bang should have created perfect, equal amounts of matter and antimatter. These opposites would have immediately annihilated upon contact, converting their mass entirely into a flash of radiation and leaving behind a vast, empty, and eternal cosmos of pure light. The fact that we are here in a universe dominated by stars, planets, and people is undeniable proof that this perfect symmetry was broken. Somehow, for every billion matter-antimatter pairs that annihilated, one single solitary particle of matter survived. That 1 in a billion survivor is the entire reason our material universe exists. The process that created this slight but overwhelmingly important imbalance is known as baryogenesis. One of the most compelling mechanisms for this is the Erfolg-Dyn mechanism, named after the physicists Ian Erfolg and Michael Dyn. It's a beautifully complex idea that emerges from the mathematics of supersymmetry. In the incredibly high-energy environment of the very early universe, the theory suggests there existed new, exotic fields associated with these hypothetical supersymmetric particles. Imagine these fields not as empty space, but as a kind of cosmic landscape with hills and valleys representing different energy states. In the first instance after the Big Bang, one of these fields, known as the Erfolg-Dyn field, could have been knocked into a precarious position, perched high on a hill in this landscape. Like a ball balanced on a peak, this state was unstable. As the universe cooled, this field began to roll down the hill, oscillating back and forth as it settled into its lowest energy state in the valley below. Now here's the critical part. The specific way this field oscillated and decayed is theorized to have preferentially produced matter over antimatter. It's as if the field, as it rattled down, shook out more quarks than antiquarks, seeding the universe with the raw material for everything to come. But the story doesn't end with just creating a surplus of matter. The decay of the Erfolg-Dyn field likely wasn't a quiet, uniform process happening smoothly everywhere at once. The rolling and oscillating of such a field can be highly chaotic, potentially creating dramatic fluctuations in the density of the matter it produced. Certain regions of space might have received a much larger helping of these new matter particles, while adjacent regions were relatively starved. This would have imprinted significant inhomogeneities, a lumpy, patchwork distribution of baryons, onto the fabric of the newborn universe. These aren't the gentle density ripples that later grew into galaxies. These are potentially much more severe variations, continents of matter in a sea of near-nothingness. Now fast forward just a few minutes to the epoch of Big Bang nucleosynthesis. The entire process is exquisitely sensitive to one parameter above all others: the local density of protons and neutrons. In the Standard Model, we assume this density was smooth and uniform. But if the Erfolg-Dyn mechanism is correct, that assumption is wrong. The universe that entered the nucleosynthesis window was already a cosmic checkerboard. In the regions where the Erfolg-Dyn decay had dumped an overabundance of baryons, the nuclear fusion reactions would have been supercharged. The high density would have allowed particles to find each other and fuse with incredible efficiency, rapidly burning through the available fuel. This might have led to a much more complete conversion of hydrogen into helium, and could have even allowed for the production of minute traces of heavier elements like lithium-7 or beryllium, pushing the nuclear reactions beyond their standard limits. Conversely, in the underdense regions, the opposite would be true. With particles spread thin, fusion would have been a sluggish, inefficient affair. The crucial deuterium bottleneck would have been even more severe, leaving behind a large surplus of unprocessed deuterium and hydrogen while producing very little helium. When we look at the universe today and measure the primordial abundances, we are not seeing the output of a single, uniform event. We are seeing the averaged out result of this wildly varying cosmic patchwork. The specific numbers we get, the 25% helium, the tiny fraction of deuterium, the puzzling shortage of lithium, could be the blended signature of these two extreme environments. The Erfolg-Dyn mechanism thus provides a profound and elegant connection. It suggests that the answer to the question, why is there something rather than nothing, might be intrinsically woven into the answer to another question. Why does that something have the specific chemical composition that it does? The two greatest mysteries of the cosmic dawn may not be separate puzzles at all, but different chapters of the same extraordinary story. To truly grasp this next concept, we need to rewind the cosmic clock even further than the quark-hadron transition, to a moment of such extreme temperature and density that matter itself ceased to behave in any way we would recognize. This brings us to a fascinating and complex idea known as the Hagedorn phase transition remnant. It's named after the German physicist Rolf Hagedorn, who in the 1960s made a startling prediction about the nature of matter under the most extreme conditions imaginable. He theorized that if you could heat nuclear matter to a sufficiently high temperature, a threshold now known as the Hagedorn temperature, something truly bizarre would occur. Instead of getting hotter, the system would hit a ceiling. Any additional energy you poured in wouldn't raise the temperature further. Instead, it would go towards creating more and more particles. It would be like trying to boil a pot of water that can never get hotter than 100 degrees Celsius. No matter how high you turn the flame, the extra heat just makes more and more steam. In this case, the steam is an exponentially growing number of hadrons, the family of particles that includes protons and neutrons. This theoretical state is often called the Hagedorn fireball, a seething, self-generating soup of matter where the distinction between individual particles begins to blur. Then, as the universe expanded and cooled past this critical threshold, this fireball would have undergone a dramatic phase transition, condensing from a chaotic plasma of hadrons into the more familiar quark-gluon plasma we discussed earlier. But here's where the theory gets particularly interesting for our story of the first elements. Phase transitions, especially dramatic ones like this, are rarely perfectly clean. Think of water freezing into ice. As it cools, it doesn't solidify into a perfectly uniform crystal all at once. Ice forms in patches with tiny bubbles, cracks, and density variations frozen into its structure. The transition out of the Hagedorn phase could have been similarly messy. As the universe cooled through this critical point, the sudden change in the fundamental state of matter could have created fossilized remnants, lingering fluctuations in density and pressure that were essentially frozen into the fabric of the ensuing quark-gluon plasma. These wouldn't be the gentle quantum fluctuations that later seeded galaxies, but potentially much more pronounced and dramatic imperfections, like cosmic scar tissue from this traumatic shift. These fossilized density fluctuations would then have been carried forward in time, persisting right through the subsequent quark-hadron transition and into the epoch of Big Bang nucleosynthesis a few minutes later. The universe that began fusing the first atomic nuclei would not have been a perfectly smooth soup. It would have been a subtly lumpy one, with some regions still slightly denser than others as a direct relic of that primordial Hagedorn fireball. The consequences for element formation are immediate. In those slightly denser pockets, nuclear reactions would have proceeded a little faster and a little more efficiently. Protons and neutrons would have found each other more easily, potentially allowing the fusion chain to run its course more completely, burning up more deuterium and producing a bit more helium. Meanwhile, in the less dense regions between these pockets, the reactions would have been more sluggish. The deuterium bottleneck might have been more pronounced, leaving behind a greater residual amount of this fragile isotope. The final, universal abundances we measure today would therefore be an average of these two different outcomes. This averaging process could potentially account for small but persistent discrepancies, like the fact that the observed deuterium abundance seems to sit right on the edge of the Standard Model's predictions, or that the lithium value remains stubbornly low. The Hadron remnant theory offers a compellingly direct connection. It suggests that the chemical fingerprints of the first 3 minutes might not just tell us about nuclear physics, but could also preserve a faint echo of the universe's state in its very first microseconds, a time when the nature of matter itself was undergoing one of its most radical and dramatic transformations. Now we arrive at a theory that fundamentally reimagines the concept of a beginning, suggesting our universe's first moments were not a unique creation event, but part of an endless, timeless cycle. This is the ekpyrotic or cyclic universe model, and it proposes a breathtaking possibility that the specific abundances of the first light elements could carry an imprint, a faint memory, of a cosmos that existed before our own. The very name ekpyrotic comes from the ancient Greek for conflagration or great fire, hinting at the dramatic transformation it describes. In this model, our Big Bang was not the absolute start of time and space. Instead, it was a violent transition, a rebirth from the ashes of a previous universe that had contracted in a cataclysmic Big Crunch. Imagine the scene just before our universe as we know it began. Instead of a singularity of infinite density, there is a vast, cold, and nearly empty space, the dissipated remains of a previous cosmic cycle. Drifting through this void are two immense, parallel three-dimensional membranes or branes, separated by a tiny gap in a higher dimensional bulk. These branes are drawn together by gravity, moving on a slow, inevitable collision course. When they finally meet, their impact is not a silent touch, but an explosion of unimaginable force. The immense kinetic energy of the collision is converted instantaneously into a seething, ultra-hot plasma of particles and radiation, flooding the newborn brain with heat and density. This collision is our Big Bang. The universe then expands, cools, forms galaxies and stars, and eventually begins the long process of fading out, its energy diluted by endless expansion, only for the cycle to eventually reverse, leading to a contraction and a final crunch that sets the stage for the next collision, the next bang in an infinite repeating loop. This cyclical view of cosmology completely reframes the question of the first elements. In the standard single bang model, nucleosynthesis had a pristine, defined starting point, a smooth, hot soup of quarks. But in an ekpyrotic universe, the material that becomes our cosmos is not pristine. It is the recycled, processed remains of a universe that lived and died before us. The primordial hydrogen and helium we attribute to the first 3 minutes might not be entirely primordial at all. They could contain a contamination, a relic abundance of elements forged in the stars of a previous cosmic cycle. This isn't just about adding a few extra atoms, it challenges the very definition of primordial. The most sensitive test of Standard Big Bang Nucleosynthesis is the exquisite prediction of the deuterium and lithium abundances. These values are a unique fingerprint tied to the specific density and temperature of our universe's infancy. If a supply of pre-existing helium, deuterium, or even trace amounts of lithium were already present when our Big Bang began, it would completely distort that fingerprint. The starting conditions for the nuclear reactions would be fundamentally different from a clean slate, but the potential influence goes far beyond simple chemical contamination. The physics of the crunch itself could have imprinted unique conditions onto the newborn plasma. As the previous universe contracted towards its finale, the unimaginable pressures and temperatures of the Big Crunch could have triggered exotic and extreme nuclear processes unlike anything in our expanding universe. These processes might have created unusual particle distributions or left behind a specific, non-thermal spectrum of radiation. When the branes collided to create our new universe, this pre-bang physics would have been baked into the initial conditions. For instance, the crunch might have left the new universe with a slightly different initial neutron-to-proton ratio, a parameter that is absolutely critical for determining the final helium yield. Even a tiny deviation would cascade through the entire 3-minute fusion process, changing the outcome. Furthermore, the cyclic model naturally produces a universe that is extremely smooth and flat, solving key problems of the Standard Big Bang model. However, this smoothing process might also erase the tiny density fluctuations that are crucial for the later formation of galaxies. To get around this, some versions of the theory introduce mechanisms to generate new fluctuations during the bounce. These mechanisms could also, as a side effect, create the kind of subtle inhomogeneities we discussed earlier, regions of slightly different density that would have experienced slightly different nucleosynthesis histories, potentially explaining the lithium problem. The profound implication of this theory is that Big Bang nucleosynthesis becomes more than just a probe of our universe's first few minutes. It becomes a potential window into the physics of the pre-bang era, a way to test the cyclic model itself. If we could find some unambiguous signature in the light element abundances that defies all explanations based on a single, isolated Big Bang, it could be the first hard evidence that our universe is just one page in an infinite cosmic storybook. The specific amounts of hydrogen, helium, deuterium, and lithium are the oldest written records we have. The ekpyrotic model suggests we might not just be reading the first chapter of our own story, but the final, faded epilogue of a tale that came before. Yet, after exploring 29 different theories, from the subtle influence of neutrino flavors to the mind-bending possibilities of higher dimensions and cyclic universes, we arrive at a concept that stands apart from all the rest. It is our idea that shifts the entire conversation from a question of mechanism to a question of meaning, and it is perhaps the most controversial and philosophically charged perspective of all. This is the 30th and final theory on our list, the anthropic principle selection. It dares to suggest that the precise, seemingly fine-tuned abundances of hydrogen, helium, and lithium might not have a detailed physical explanation at all. Instead, it proposes that these values are what they are for one simple, staggering reason, because they allow for us to be here to observe them. The anthropic principle comes in several varieties, but its core logic is deceptively simple. It begins with the observation that the universe appears to be remarkably well suited for the emergence of life. The fundamental constants of nature, from the strength of gravity to the mass of the electron, seem to be perfectly calibrated to allow for the formation of stars, planets, and complex chemistry. If any of these values were even slightly different, the universe would be a lifeless void, no atoms, no stars, no planets, and certainly no cosmologists to ponder the mystery. The weak version of the anthropic principle simply states that we must account for this observational selection effect. When we measure the universe, we are inevitably observing it from a privileged position, one that is compatible with our existence as conscious observers. We could not possibly find ourselves in a universe that does not allow for life. Now, apply this logic to the outcome of Big Bang nucleosynthesis. The Standard Model predicts the primordial abundances with breathtaking accuracy, but it relies on one crucial input, the density of ordinary matter in the early universe. That density, in turn, is not predicted by the model. It is a number we must measure from observation and plug in, and that number seems to be just right. If the matter density were significantly higher, the nuclear reactions would have proceeded with overwhelming efficiency, converting nearly all the hydrogen into helium. A universe without hydrogen is a universe without water or organic chemistry, a universe almost certainly devoid of life as we know it. Conversely, if the matter density were much lower, the fusion reactions would have been anemic and inefficient. The universe would be left with almost nothing but hydrogen, with far too little helium to seed the formation of massive stars that forge the heavier elements essential for planets and life. The process would also have left behind a disastrous overabundance of deuterium, which would have altered the entire future evolution of stars, likely making them burn out far too quickly for life to ever arise. The anthropic principle takes this apparent fine-tuning and offers a radical explanation. Perhaps there isn't a single, unique physical reason why the matter density has the value it does. Instead, maybe there exists a vast multiverse, a colossal ensemble of universes, each with its own random set of physical constants and initial conditions. In the overwhelming majority of these universes, the density parameter is all wrong. Big Bang Nucleosynthesis produces a sterile, lifeless cosmic recipe. Hydrogen is entirely consumed, or deuterium floods the cosmos, or no helium is made to fuel future stars. These universes are stillborn, destined to never host a single thought. But in an incredibly tiny fraction of these universes, by sheer chance, the dice roll just right. The matter density falls within the narrow, golden range that allows for a balanced outcome. Plenty of hydrogen for water and life, enough helium to build stars, and just the right amount of deuterium to not interfere. We, of course, find ourselves in one of those exceptionally rare, bio-friendly universes. We don't observe the typical outcome of BBN. We observe the only outcome that could possibly lead to us. This is not so much a theory that explains how the light elements got their abundances, but rather a framework that explains why we shouldn't be surprised that they seem so perfectly set up for life. It dissolves the fine-tuning problem by distributing it across an infinite landscape of cosmic failure. For some scientists, this is a profound and elegant solution, the ultimate expression of cosmic humility. For others, it is a philosophical cop-out, a retreat from the physicist's duty to find a precise causal mechanism within our own universe. They argue it makes science untestable, as any apparent coincidence can be explained away by invoking an infinite number of unobservable alternate realities. Yet, even as a controversial last resort, the anthropic principle forces a breathtaking shift in perspective. It suggests that the ancient atoms of hydrogen and helium that make up 99% of everything we are, the very atoms we use to measure and ponder the cosmos, are themselves the ultimate selection effect. They are not just the silent architects of stars and life, they are the signature of a universe that was, against all odds, capable of asking the question. And so we find ourselves at the end of this cosmic journey, having ventured through 30 different windows into the universe's very first moments. From the elegant, established framework of Big Bang nucleosynthesis to the wildly speculative realms of extra dimensions and cyclic universes, the diversity of thought is nothing short of breathtaking. We've explored how subtle tweaks, a different neutrino flavor here, a slight magnetic field there, could alter the entire cosmic recipe. We've considered the possibility that dark matter itself, in the form of actions, might have left its fingerprint on the first atoms, and we've dared to imagine that the answers might lie in a reality with more than 3 spatial dimensions, or even in the echoes of a universe that existed before our own. What's truly remarkable is that each of these theories, whether it ultimately proves to be correct or not, serves a profound purpose. They are not just flights of fancy, they are stress tests for our understanding of reality. Each one pushes the boundaries of physics, forcing us to ask deeper questions and to look at the oldest light in the universe with fresh, curious eyes. They deepen our wonder, reminding us that the story of the first 3 minutes is not a closed book but a living, breathing mystery, the greatest detective story ever told. The fact that we can even conceive of such ideas, from the quantum dance of neutrinos to the gravitational stirring of primordial black holes, is a testament to the incredible power of the human mind to reach back across 14 billion years and touch the dawn of time itself. The search is far from over, In fact, we are on the cusp of a new era of discovery that promises to shed light on these very questions. Next-generation observatories like the James Webb Space Telescope will peer back at the first galaxies with unprecedented clarity, analyzing the chemistry of the most ancient stars to look for any deviation from the predicted primordial abundances. On Earth, immense particle colliders continue to push energies higher, searching for signs of supersymmetry or other new physics that could have played a role in the early cosmos. And precision cosmology experiments are measuring the faint afterglow of the Big Bang, the cosmic microwave background, with ever greater accuracy, searching for the faint imprints that gravitational waves or early dark energy might have left behind. The mystery of the first light is a puzzle that connects the smallest particles to the largest scales of the cosmos, and solving it will require all of our ingenuity. Perhaps the answer lies with one of the theories we've discussed today. Perhaps the true explanation is something we haven't even dreamed of yet. That's the thrilling nature of science. It's an endless frontier. So we want to know which of these cosmic origin stories captures your imagination the most. Does the subtle influence of neutrino oscillations intrigue you, or are you drawn to the grand drama of the ekpyrotic cyclic model? Let us know your thoughts in the comments below. We're just as fascinated to hear your perspective on